Imagine 3 optical benches in 3 different labs. On the first, a sample of molybdenum disulfide, tape pulled from a crystal, sits under a microscope while a halogen lamp spills white light onto it. On the second, a beam of laser light bounces off a gold-patterned chip, and the reflection is dispersed not by wavelength alone, but by the angle it leaves the sample. On the third, a stack of atomic thickness layers, a van der Waals sandwich, is mounted vertically on a rotation stage, with a femtosecond laser firing from below. All 3 setups, despite their different ambitions, are built around the same physical trick, and in 2 of them, that trick depends on a single lens. This pulls together 3 papers. The first is Frisenda and colleagues, published in the Journal of Physics D, Applied Physics in 2017, which lays out, with a full bill of materials, how to build a micro-reflectance and transmittance microscope for 2D materials for under €9,000. The second is the 2024 review by Cueff, Bergiga, and Nguyen in Nanophotonics, which explains the physics of Fourier imaging and gives the canonical recipe for angle-resolved spectroscopy. The third is a recent paper by Sortino and colleagues on van der Waals heterostructure metasurfaces, where we focus narrowly on the optical bench they constructed to characterize their samples. The 3 together form a build progression, from a simple modified commercial microscope to the canonical angle-resolved rig to a custom vertical mount metasurface station. Standard optical spectroscopy gives you intensity versus wavelength. That's enough for many problems, but it throws away one critical dimension: angle. Light scattered from a nanostructure carries information not just in how much energy is emitted, but in which direction it goes. As Cueff and colleagues stress, conventional ellipsometry only collects the specular reflection, and conventional spectroscopy collects all angles but sums them at the detector. Either way, the angular distribution is lost. For the new generation of nanophotonic devices, metasurfaces, photonic crystals, bound states in the continuum, that angular information is the experiment. The fix turns out to be remarkably simple. A converging lens, by its very nature, performs a 2-dimensional Fourier transform on the light field passing through it. Every plane wave leaving the sample at a particular angle is focused to a particular point in the back focal plane of the lens. So if you image the back focal plane, sometimes called the Fourier plane, instead of the sample, you read off the radiation pattern directly. That's the entire trick. Most of the cleverness in these papers is in deciding what else to put in the optical path. Let's start with the most accessible setup. Frisenda and colleagues wanted micro-reflectance and transmittance spectroscopy on 2D materials with about 1 micron lateral resolution in the visible and near-infrared. Their setup, shown in Figure 2, is essentially a commercial metallurgical microscope with a clever modification of the trinocular port. Here's the build, step by step. Start with a Modic BA310 metallurgical microscope. That gives you epi-illumination and a long working distance 50 times objective with numerical aperture of 0.55. To the C-mount trinocular port, you attach a 90-10 beam splitter cube inside its mount using an adapter. The beam splitter divides the light leaving the microscope into 2 paths. 10% goes to a CMOS camera, that's your sample viewing image, mounted on a short SM1 lens tube. The other 90% goes upward through an XY translation stage, then a focusing stage, into the polished end of a multimode fiber with a 105 micron core. The fiber's other end is plugged into a Thorlabs CCS200 fiber-coupled CCD spectrometer. The genius of the design is the fiber as pinhole. Because the multimode fiber sits in the image plane of the microscope, its core acts as a confocal aperture. Light is only collected from the small patch of sample that the fiber face is imaging. To align it, you reverse the trick. You temporarily plug the fiber into the halogen lamp, which projects an image of the fiber's core down onto the sample. You use the XY stage to center that bright spot on the camera's crosshair, and you use the focusing stage to bring it sharply into focus. Then you disconnect the lamp, plug the fiber back into the spectrometer, and you're ready to record. Reflectance uses the microscope's own epi-illumination with the field aperture closed to about 60 microns. Transmittance is done by turning off the lamp, putting the sample on a homemade brass holder and feeding white light up through the sample from a halogen source coupled to a fiber bundle directly beneath it. The full bill of materials totals around €8,500. Frisenda and colleagues used this rig to determine the number of layers in molybdenum disulfide, tungsten disulfide, tungsten diselenide, and molybdenum diselenide from the energy of their excitonic peaks to characterize the so-called A, B, and C excitons across mono and multilayer flakes, and to scan 116 CVD-grown molybdenum disulfide crystallites and show statistically just how uniform the chemical vapor-deposited material was. Now, the Frisenda rig collects light from a single spot, but doesn't resolve where an angle it came from. For that, you need the canonical Fourier imaging configuration described in the Cueff review and shown in Figure 3. Start again with a high numerical aperture objective. The excitation source comes in through a beam splitter and is focused onto the sample. The scattered or reflected light returns through the objective. Now here's the key addition. Instead of imaging the sample directly, you place a Fourier lens one focal length behind the objective's back focal plane. That lens projects the back focal plane, the Fourier space, onto an intermediate image. At this intermediate plane, the spatial coordinates of your image are real space coordinates, so you can drop a spatial filter here to block, say, the specular reflection from the excitation beam, or to select only a small region of the sample. A second lens, the focus lens, then re-images the Fourier plane onto a final imaging plane. The imaging plane is positioned at the entrance slit of a spectrometer. The slit acts as a one-dimensional spatial filter that selects a single line in the Fourier plane, that is, a single value of one momentum component, say ky. The grating inside the spectrometer disperses that line along the energy axis, and the CCD camera records the result as a two-dimensional image, energy on one axis, in-plane momentum kx on the other. That's an energy-momentum dispersion measurement in a single shot. To scan the other momentum direction, you just translate the focus lens laterally by a small distance, delta. That shifts which slice of the Fourier plane lands on the spectrometer slit. Sweep that translation, stack the resulting dispersion images, and you've reconstructed the full three-dimensional band diagram of your sample. This is the recipe behind a remarkable variety of experiments. The Cueff review walks through measurements of polarization vortices at bound states in the continuum, observations of topological edge states in photonic crystals, demonstrations of the photonic spin-Hall and Rashba effects, and even an analog acoustic black hole built from a flowing polariton fluid. All of them rely on the same core architecture, sometimes with added polarization optics, sometimes with an infrared for phase, but always the same backbone. Now for an instructive variation. Sortino and colleagues needed to characterize gold-patterned van der Waals heterostructure metasurfaces, both their reflectance angular dispersion and their photoluminescence emission. Their setup, in Figure 4, is a custom home-built rig that takes the canonical recipe and adapts it for two-sided sample access. Here's what's different. The sample is mounted vertically on a rotation stage, so its long axis can be aligned with the vertical slit of the spectrometer above it. From the side, a halogen lamp shines into a beam splitter that directs white light up through a high numerical aperture objective, a 60 times with NA of 0.95, onto the sample from below. The reflected signal is collected back through the same objective. Above the objective is the 4F imaging arrangement. A Bertrand lens sits one focal length above the back focal plane. A tube lens sits beyond that, separated by twice its own focal length from the Bertrand. Together, they form a 4F system that projects the back focal plane image onto the spectrometer slit. To switch from angle-resolve spectroscopy to ordinary microspectroscopy of the sample's real space image, you simply remove the Bertrand lens. The tube lens then images the real plane of the sample onto the slit instead. For photoluminescence work, the excitation source is on the opposite side. A frequency-doubled, femtosecond pulsed titanium sapphire laser at 405 nanometers comes in from below through a 10 times NA 0.25 objective in transmission geometry. The PL emerges upward through the sample, through the high NA objective, and into the same collection arm.
With this rig, Sortino and colleagues demonstrated strong coupling between the metasurface's quasi-bound state in the continuum mode and the tungsten disulfide monolayer exciton, mapped the polariton dispersion, and observed nonlinear blue shifts of the polariton emission at high pump intensities.
What unites the three builds is a progression in ambition. Frisenda's rig adds a beam splitter and a fiber to a standard microscope and gets you wavelength-resolved spectra of 1-micron spots. The canonical setup, described by Cueff, adds a Fourier lens, a focus lens, and an imaging spectrometer, and gets you energy-momentum dispersion in a single shot. Sortino's custom variant adds a vertical sample mount, separate transmission excitation, and a removable Bertrand's lens, and gets you angle-resolved reflectance and PL on the same bench.
Each layer of complication unlocks one more dimension of light, first wavelength, then angle, then polarization, phase, and time. The same physical principle that a lens computes a Fourier transform underlies every step.
None of these setups is optimal for all tasks. Frisenda's fiber-coupled rig cannot resolve angles. The canonical Fourier setup uses objectives optimized for real space imaging, not for Fourier imaging, so the angular resolution is limited by aberrations at the back focal plane. And the Sortino rig, wonderful for transmission samples on glass, would not easily accommodate, say, an opaque substrate. The Cueff review points toward future improvements: purpose-built Fourier objectives, meta-surface-based Fourier lenses for wider angular collection, and birefringent interferometers that capture energy and momentum dispersion in a single shot. 3 setups, 3 levels of complexity, 1 unifying idea. If you take nothing else away, take this. A lens is not just a focusing element, it is a Fourier transformer. Once you accept that, you can read every angle of every photon leaving your sample. From a modified commercial microscope to a vertical mount metasurface bench. That is the technology underneath modern nanophotonic spectroscopy. Now, a few comprehension questions to check your understanding. Question 1. What component in the Frisenda micro-reflectance setup acts as a confocal pinhole, and how is its position on the sample determined? Here's the key idea. It's the core of the multi-mode fiber. To align it, the free end of the fiber is temporarily connected to the halogen lamp, projecting an image of the fiber core down onto the sample. The X, Y, and focusing stages then center and focus that spot on the camera crosshair. Question 2. Why does a single lens naturally produce an image of the angular distribution of light at its back focal plane? Here's the key idea. Each plane wave leaving the sample at a particular angle is focused by the lens to a specific point in the back focal plane. Mathematically, the field at the back focal plane is the 2-dimensional Fourier transform of the field at the front focal plane. So position in the back focal plane corresponds to direction of propagation. Question 3. In the canonical angle-resolved setup, what is the role of the spatial filter placed at the intermediate image plane, and why is the slit of the spectrometer placed at the final imaging plane? Here's the key idea. The intermediate image plane is in real space, so a spatial filter there can block specular reflections or select a small region of the sample. The final imaging plane is in Fourier, or momentum space, so the spectrometer slit selects a single value of one in-plane momentum component, and the grating disperses that line along the energy axis to give a one-shot energy-momentum dispersion image. Question 4. What is the purpose of mounting the sample vertically in the Sortino metasurface setup, and what does removing the Bertrand lens accomplish? Here's the key idea. Vertical mounting lets the metasurface's long axis align with the vertical spectrometer slit, so the slit acts as a spatial filter for one-shot angle dispersion. Removing the Bertrand lens converts the optical train from Fourier plane imaging back to conventional real space microspectroscopy of the sample. Question 5. What trade-offs does the Frisenda setup make compared with the Sortino or canonical angle-resolved setups? Here's the key idea. The Frisenda design is cheap, under €9,000, uses an off-the-shelf commercial microscope, and is easy to replicate, but it collects light from a single spot via the fiber and cannot resolve the angular distribution. The angle-resolved setups are more expensive and require custom assembly, but they unlock momentum, polarization, and phase-resolved measurements. Question 6. In Sortino's setup, why is the photoluminescence excitation introduced from below the sample rather than through the same objective used for collection? Here's the key idea. A transmission geometry separates the excitation laser path from the collection path, which simplifies rejecting pump light from the measured PL signal, and lets a different, lower NA objective deliver the femtosecond laser, while the high NA objective is reserved for collecting and Fourier imaging the emission. And that's the whole tour. 3 benches, 3 levels of complexity, 1 lens doing the magic.